We will check on this. If again, if the meeting is reconnecting, happening again, then we can switch to Google Meet. So from today, we can start software engineering. Important and easy ways to get marks from software engineering. We have models from the model itself, from the software development model itself. We can gather all the necessary steps, and then into testing, design principles, testing, coding standards, maintenance, calculating staffing profiles, COCOMO model. So from the beginning, from the model itself, from the software development model itself, we can inherit more knowledge about software engineering. So first we will check the basic models. I didn't add agile methodology, so we will add agile methodology later and continue with this because I couldn't find any suitable notes for agile methodology for the given questions for the few years. So we'll add comprehensive and important notes in the for agile methodology. So we will start about software engineering. We knew that software is a passive software. It's not just a program code. It have data sections, executable codes, files. So a software is more than just a program code. A software is just more than just a is more than just a program code. Software is considered to be a collection of executable programming code, associated libraries, and documentations. Software, when made for a specific requirement, is called software product. Okay. Then engineering, on the other hand, is all about developing products using well-defined scientific development of software product using and methods. So we can define software engineering as an engineering branch associated with the procedures. The outcome of software engineering is an efficient and reliable software product. The IEEE defines software engineering as application of a systematic, disciplined, quantifiable, quantifiable approach to the development, operation, and maintenance of software. So, whether we need software engineering approaches, a systematic scientific approach for a small project, there is no need for a software engineering approach. But if the project is large, if the project have more modules, if the project have huge complexity, then there is a need for software engineering methodology to be included. It's all about developing a project in a systematic manner. Okay, because software is an intangible product. Software is an intangible product. So we cannot able to see how much work have been done, how much work completed, how much work needs to be completed. So there is a need for a structure. There is a need for an approach to follow because we have team to be followed. We have members to be followed with many knowledge levels, experience level. So we also needs to consider risk after we taking the projects. So yeah, software engineering principles is necessary to complete a large and complex projects. So important, we have software engineering. First, it helps to reduce the programming complexity. We have two principles to reduce this programming complexity, which includes if it is a large project, abstraction and decomposition. Abstraction, we know that from object-oriented programming concept, abstraction is about showing only relevant details to the user and hiding irrelevant details. So here, what we are going to do is we are going to consider only relevant problems that are relevant for certain purpose and suppress other aspects that are not relevant for the given. Once the simpler problems are solved, the omitted details can be taken into consideration to solve the next level of abstraction. Abstraction is a powerful way of reducing the complexity of the problem. Complex problems is divided into several smaller problems, and then smaller problems are solved by decomposition. So abstraction, what we are going to focus on important or core problems, and then we can add later by using integration techniques. And decomposition is just like divide and conquer. Here it's the division. The decomposition is important. Just if we decompose randomly, it is not the best way to uh, reconstruct the project. So division is important. How we are making the how we are decomposing the process. Decomposing the problem and solves the problem one by one and integrate. A good composition of a problem should minimize interaction among various components. We have two concepts, cohesion and then coupling. Cohesion and then coupling. We will see it later in design principles. So what is the need for software engineering? First one, large software. If the software is large, there is a need for engineering principles to be taken in a scientific approach. Then scalability. If the software process were not based on scientific and engineering concepts, it would be easier to recreate new software than to scale an existing one, like uh, legacy products, legacy softwares, re-engineering principles. We need to look up. Then cost. We must be able to forecast how much the product would cost, how much salary would cost for a team. So we need to consider everything. Then dynamic nature. Based on requirements, the software requirements can be changed during development itself. Software requirements can be changed. We have models like agile methodology. We have agile nowadays. Agile methodology have been used by almost all IT companies because the requirements can be changed during the development. So there should be a dynamic approach. There should be a dynamic way to revert back or roll back, or based on requirements we can change the products. Then quality management. For a better process of software development, it provides better and quality products. We will see quality management and then uh, software quality, total quality management. That. And then the quality like ISO standards, KPI standards, like those we have to look up. Then what are the characteristics of a good software? It can be justified. A software can be the software must satisfy on the following grounds. It should be operational, it should be transitional, and should be maintained. Here, operational means that it tells us how well software work in operations. It can be measured on budget, usability, efficiency, correctness, functionality, dependability, security, and then safety. Transitional means that maintenance, like portable, adaptive maintenance. So this aspect is more important when the software is moved from one platform to another platform. Portability, and then interoperability, reusability, very important, reusability, adaptability. Maintenance, uh, like we need to from the beginning itself, from the coding itself, we have to document everything from internal documentation to external documentation, from naming variables, functions. From there itself, maintenance starts. This aspect briefs about how well a software has the capability to maintain itself in the ever-changing environment, which is modularity, maintainability, flexibility, scalability. In short, software engineering is a branch of computer science which uses well-defined engineering concepts required to produce efficient, durable, scalable, in-budget, on-time software products. Then we will see software development life cycle, which is the basic concepts, life cycle model, a process model. Okay, here we can see what is the need for a software life cycle model. Yes, perform uh, we can perform without using a software development model, without using any model like waterfall model, prototype model, iterative model. We don't need anything if the project is smaller, if the software is smaller. But if it is complex, it have complex problems, then there is a need. And if the principles is followed by the software engineering, if the software companies, then they can reuse the components. They can make a scale out of it. So whether there should be a decision taken for engineers whether it is feasible. What happened if there is a requirements change? What happened after 10 years? There is a maintenance. If there is no documentation properly managed, then management would be a headache. So there is a need for a software development life cycle model. We have different level of life cycle models. The basic one, classical waterfall model. Classical waterfall model it is a theoretical way of developing a software. But all life cycle models are essentially derived from classical waterfall model. It is not practically used. Classical waterfall model or sequential model, it is not def- it's not in practical. It is not practical to use. Mostly, we can say that a small project, a school, college level, UG level project can be possible, but it is not possible in software companies by using this waterfall model. But the steps are necessary. They That's actually the structure. The classical waterfall model is the basics for all other models. Whatever the waterfall model holds as the phase, that is also applicable to all other phases, but there is a slight changes in so like prototype model. The same feasibility study, same requirements gathering is again same in all other models. Like in here, we can see that feasibility study to determine whether it would be financially and technically feasible to develop a product. This happens in all waterfall models by gathering, uh, by using historical data, by having knowledge of senior engineers. There should be assessment about whether we can complete the project on our own, or number of projects that we have done in the past based on previous knowledge, based on historical knowledge, based on experience. This feasibility study is conducted. Okay, here also there. Uh, okay, there should be a meeting between the client and then programmers or a senior programmer. They investigate they understand the problems and investigate possible solutions, and they make a plan, an agreeable plan. Then they would start development process. Then requirement analysis, specification. The most important part here is the requirement analysis and specification. Even sometimes the client cannot able to express their needs, their requirements. In that cases, we can use prototype models like this. In this phase, we have two distinct activities. One is requirement gathering and analysis, and then specification using SRS document. Okay, first we will gather and analyze. We understand the problem. Then we file them. Then we make them as a document to verify it later after the system have been completed, after the system have been deployed. So we can verify the requirement specification document later to make it as acceptable product. Okay. So here uh, the important components of these documents are functional requirements, non-functional requirements, and then goals of implementation. You will see software requirement specification in detail because how SRS is happening, how requirements gathered, either interview or group discussion. either or questionnaire, and how it is structured, whether it is concise, whether it is ambiguous, we will see later. And then design phase. After filing, after making a document about requirements, then we move to the implementation. There are two approaches for design. One is traditional design approach, which is sequential in manner. The design and a design approach which is sequential in manner, whether it is top down or bottom up approach. Top down approach or bottom up approach. Then okay. Okay, then object-oriented design approach where problems are each problem is constructed as an object, a real-life entity. So we solve each object, and then together we can make a module of that. That's another design approach. And then coding and unit testing. Coding here means the actual implementation phase. Coding here is an actual implementation phase of software development to translate the software design into source code. Okay. There are some guidelines to be followed. We will check it later. The coding is like choosing which programming language is better for that particular project. Either if it is web application, then we can go for either JavaScript or ISP or PHP. Then we can choose if it is app. Then we can choose either it is Python, Flutter, Node.js, or sorry, Java, or we need C or C++. There should be a discussion around coding, and there should be also a coding standards needs to be followed, like naming variables and also internal documentations about what is the functionality of the where we should describe the functionality of the function. That's like that. And then unit testing means the unit, a single unit as a program, whether it is working fine, as a module, whether it is working. Then integration and system testing, whether it can be step-by-step approach or it can be a big bang approach. We just integrate everything and start working. And also step-by-step integration is preferred. During each integration step, the partially integrated step system is tested and a set of previously planned modules are added. Finally, we will have whole system. That system conforms its requirements laid out in the SRS document. Okay, so we have a unit, a program, or a module. Then we are going to integrate them. During integration, we need to check the parameters, database access. That part during integration, we will check cohesion, whether a single module is working perfectly without interacting with other modules. That high cohesion high cohesion program is needed for design. That is what we have to do. And then system testing, which actually the whole completed software product that checked against SRS document, that we have a document filed by collecting customer requirements. Those customer requirements are documented by functional, non-functional requirements of the software product. Then that document is verified. Those requirements have been met or not in the system, in the developed software. That is system testing. We have three types of testing. One is alpha testing, which the testing performed by the development team itself, If the developed system is tested by the developer team, then it is alpha testing. Then there is a special case of beta testing. By testing, the system testing is performed by a friendly set of customers. After development, the unreleased version or beta version is given to their set of customers. Like beta, we are in real life we have seen beta version of the software. So based on customers' feedback, there would be a change. There would be modifications on the software product. That is beta testing. Testing performed by friendly set of customers. And then acceptance testing, which is tested against SRS document. The system testing performed by the customer himself after the product delivery to determine whether to accept or to reject the delivered product. Okay. So system testing, alpha testing, beta testing, and then acceptance testing. And then maintenance part. Here you can see the development. If here the maintenance effort is 60% of development. Only 40% is development, 60% is maintenance. Okay. So maintenance involves performing any one or more of the following three kind of activities. Corrective maintenance, either corrective maintenance, then perfective maintenance, and then adaptive maintenance. Here in corrective maintenance, we are going to correct errors that are not discovered during the project development phase. That is corrective maintenance. And then perfective maintenance based on requirements of the customer. We are going to enhance, we are going to change the content of the product, content of the software. That is perfective maintenance based on customers' requirements, called as perfective maintenance. And then adaptive maintenance, like uh, like uh, hardware changes, software updates, those are adaptive maintenance. Here, porting the software to work in a new environment, or then porting may be required to get the software to work on a new computer platform or with a new operating system. This is called adaptive maintenance. The shortcomings of the classic waterfall includes it is not possible, it is not practically possible to commit the requirements laid out by the customer in the beginning itself. Maybe the requirements can be changed. If the requirements have been changed, there is no possible way to go back and change the requirement, and we have to start over and over again. So this classical waterfall model is not practically applicable because requirements can be changed. So it's not possible. And also then in order to overcome this issue, we have iterative waterfall model. There is a feedback path, same as a waterfall model, but with the feedback path. Here, the feedback path provided for error correction and as when detected later. So even though errors are inevitable, but it is desirable to detect them in the same phase in which they occur. So this can reduce the effort to correct the bugs. Okay, there is a feedback path given. The advantageous model is that there is a working model of the system in a very early stage of development, which makes it easier to find functional or design flaws. Finding issues at an earlier stage of development enables to take corrective measures in a limited perspective. The disadvantages with this model, it is applicable to only large and bulky software development projects. This is because it is hard to break a small software system into further small serviceable modules. So the iterative software development model is suitable only for large projects, not suitable for small projects. Then prototyping development model. Here, if the customer is not sure about requirements, if the customer doesn't know the requirements, if the customer doesn't never seen a system before, so there is a need for a customer to understand the requirements, for a customer to understand the problem. Then only he can give a clear picture of his requirements. So there is a need for a prototype. Yes, working model with limited functional capabilities, low reliability, and inefficient performance compared to actual software. A prototype is usually built using several shortcuts, like using stub procedures, and then using stub procedure, which actually which actually just just provides exact results, not in actual results. This shortcut might involve using inefficient, inaccurate, or dummy functions, such as stub procedures. The shortcut implementation of a function, for example, may produce the desired result by using a table lookup instead of performing actual computations. The prototype usually turns out to be a very crude version of the actual system. What is the need? What is the need? There are several uses of prototype here. It is to illustrate input data format. To illustrate input data format, messages, reports, and interactive dialogue with the customer. It is very much needed to gain better understanding of the customer needs, how the screen might look like, how the user interface would be, how the system would produce output. It is also why another reason is also it is impossible to get perfect product at first time. Okay. So the experience guide in developing the prototype can be used to develop the final product. A prototyping model can be used when technical solutions are unclear to the development team. If the technical solutions about the product is not clear, then they can use a prototype model. The prototype can help engineers to critically examine the technical issues associated with the product development. Often, major design decisions depend on issues like the response time of the hardware controller, efficiency of the sorting algorithm. In such circumstances, a prototype may be best or the only way to resolve the technical issue. Okay. A prototype of the actual product is preferred in situations such as user requirements are not complete or not known. Are not known. If we cannot able to understand user requirements or the user does not able to give the exact requirements, then there is a need for prototype. And if the development is not clear about technical issues, technical aspects, then there is a need for prototype development to understand what is the basic fundamental problem, the technical issues with the product. Then they can throw the prototype away and they can start building. Okay, here we can see initial requirements such as SRS documents have been developed, and the design process, prototyping, customer evaluates the prototype, then we are going to review and update, and then again going to design. This process continues until the customer is satisfied. Then we can start the actual development. Then we can start develop the product. Then we test and deploy the product. Another one, evolutionary model, also known as successive version model or incremental model. Here, a simple working model is built. Subsequently, it undergoes functional improvements. We keep on adding new functions till the desired system is built. Here, we are going to build a software with core functionalities. We are going to deliver it to the customer. And the customer start using the product, whether the software is still is in development. Okay. Then we keep on improving. Just we are going to evolve. We are going to add features to the prototype, to the software. The applications include large projects where you can easily find modules for incremental implementation, often used when the customer wants to start using the core features rather than waiting for the full software. So the customer no need to wait for the full software. If he gets the core functionality, he can start working before even he deploy the product. Also used in object-oriented software development because the system can be easily portioned into units in terms of objects. Advantages include the user gets a chance to experiment partially developed system. It is advantages. Reduce the error because core modules get tested thoroughly. Disadvantages include it is difficult to divide the problem into several versions that would be acceptable to the customer, which can be incrementally implemented and delivered. We have to deploy many versions. Again, here, software concepts, requirements analysis. And then designing, we are going to develop a system, deliver the version to the customer give the feedback, and then based on customer feedback, we are going to develop the system. After that, final acceptable product is developed. Okay. Then spiral model, which have only risk assessment. Among the basic traditional models, software spiral model holds the risk assessment. This here in this figure itself, we can see the model appears like spiral with many loops. The exact number of loops in the spiral is not fixed. Each loop of the spiral represents a phase of the software process. For example, innermost loop might be concerned with feasibility study, the next loop with requirement specification, the next one with design, and so on. Each phase in this model is split into 4 sectors. Here you can see first quadrant, objective setting. What we are going to do is we are going to collect the requirements, we are going to set the objectives, then we can go to second quadrant, risk assessment and reduction. During the first quadrant, it is needed to identify the objective of the phase, examine the risk associated with these objectives. And then in second quadrant, we are going to assess the risk and reduce the risk. A detailed analysis is carried out for each identified project risk. Steps are taken to reduce the risk. Here, for example, if there is a risk that is requirements are inappropriate, a prototype system may be developed. Okay. Then in the third quadrant, we are going to develop the product again with the design phase, code phase, integration phase, test phase, and then implementation phase. Develop and validate the next level of the product after resolving the identifier risk in the second quadrant. And then in fourth quadrant, we will have a full software, and then that software can be reviewed. Based on feedback, we can plan the next loop. In fourth quadrant, review the results achieved so far with the customer and plan the next iteration around the spiral. By using review and planning, we can progressively more complete version of the software gets built in each iteration around the spiral. Circumstances to use spiral model. When we can use the spiral model. Here you can see spiral model is called meta model since it encompasses all other life cycle models. Risk handling is inherently built into this model. The spiral model is suitable for development of technically challenging software products that are prone to several kinds of risks. However, this model is much more complex than other model. That is, this is probably the factor deterring its use in ordinary projects. It's much more complex. They have risk assessment, and then it can be used for technically challenging products, software products. Comparison of life cycle models includes like a classic waterfall model can be considered a basic model to all other life cycle model. However, the classic waterfall model cannot be used in practical development products. And then this problem, which means that it have no feedback mechanism to correct the errors committed during the development phase. This problem is overcome in the iterative waterfall model. There is a feedback path and also it is a widely used software development model evolved so far. This model is simple to understand and use. However, it is suitable only for well understood problems. It is not suitable for very large projects and for projects that are subject to many risks. Okay. Then prototyping model is suitable for which either the user requirements are not clear and technical aspects are not well understood. This model is especially popular for development of user interface part of the project. The evolutionary approach is suitable for large problems which can be decomposed into a set of modules for incremental development and delivery. This model is also widely used for object-oriented software development projects. Of course, this model can only be used in incremental delivery of the system acceptable to the customer. The spiral model is a meta model. It encompasses all other life cycle models, whatever in all other life cycle model phases that are available in meta. Risk handling is inherent into the model. The spiral model is suitable for development of technically challenging software products that are prone to several kinds of risks. This is much more complex model than this model is the fact. This is much sorry. This is a much more complex model. That is the exact problem by using not using this model because it is too much complex. Okay. So based on requirements, we can choose which product model, which process model we can use based on requirement, based on customer's point of view, incremental development, and then requirement specifications, technical feasibilities, risks. So we can choose either any of them. Then first phase we have seen requirements analysis and specification. Before we start to develop our project, it becomes quite essential for us to understand and document the exact requirement of the customer. Who is doing this? Experienced member of the development team. They are called system analysis. Okay. The analysis states requirement gathering and analysis activity by collecting all information from the customer, which should be used to develop the requirements of the system. He then analyzes the collected information to obtain a clear and thorough understanding of the product to be developed, with a view to remove all ambiguities and inconsistencies from the initial customer perception of the problem. Here, these are the questions to be answered and then to be fed. Basically, what is the problem? Why it is important to solve the problem? What are the possible solutions for the problem? What exactly are data inputs to the system, and what exactly data output by the system, like black box? What are the likely complexities that might arise while solving the problem? Risk. If there are external software or hardware with which the developer software has to interface, then what exactly would the data interchange formats with the external system be? These are the sample questions. So analyst understood the exact customer requirements. Then he proceeds to identify and resolve various requirements problems. The most important requirements problem that the analyst has to identify and eliminate are the problems of anomalies, inconsistencies, and incompleteness. Further, when the analysis detects any inconsistencies, anomalies, and incompleteness in the gathered requirements, he resolves them by carrying out further discussion with the end user. What are the parts of the SRS document? Functional requirements are the system, non-functional requirements of the system, and goals of implementation. Functional requirements includes like programming language, and then maintenance. Here, non-functional requirements, maintenance, not maintenance. Maintenance such as testing, test cases, those are functional requirements. Functional requirements here, you can see it's like black box view. Functional requirements is black box view. The functional requirements part discusses functionalities required from the system. A system is what we are going to do is input, output, and functionality. It's like black box view. It's like work done using high-level functions. The non-functional requirements, such as maintainability of the system, portability of the system, usability of the system. Here, goals of implementation includes the implementation part documents some general suggestions regarding development. These suggestions guide trade-off among design goals like risk associated. The goals of implementation section might document issues such as revisions to the system functionalities that may be required in the future, new devices to be supported in the future, reusability issues in the next. These are the items which the developer might keep in their mind during development so that the development system may meet some aspects that are not required immediately. Identifying functional requirements from the problem description. Okay, so we have documented the SRS. Okay. So how we are going to identify functional requirements of the problem description? Here we can see that here we can use like yes. Consider a case of library system. Function is to search book function. So the function here is to search search the book where it is located by giving author name, uh, by giving author. So we can give author's name as an input. Then we can find the details of the author's book and location of these books in the library. So the function search book here, function here is search book. Takes the author's name and transforms into a book detail. Functional requirements actually describe a set of high-level requirements where each high-level requirements takes some data from the user and provides some data to the user as an output. Also, each high-level requirement might consist of several other functions. So, what are the properties of the good software requirement specification document? It should be concise and at the same time unambiguous. At the same time, unambiguous, should be consistent and then complete. Verbose and irrelevant descriptions reduce readability and also increase error possibility. Then it should be structured. It should be structured because we need to verify it. A well-structured document is easy to understand and modify. In practice, the SRS document undergoes several revisions to cope up with the customer requirement. Often, the customer requirements evolve over the period of time. Therefore, in order to make the modifications, the SRS document should be structured, well structured. And then you should have a block box view, which means it shouldn't discuss about implementation. It shouldn't discuss about technical aspects. It should discuss about what the system would do. It is not going to discuss about how it will perform the operations. Here, it should only specify what the system should do and refrain from starting how to do this. This means SRS document should specify the external behavior of the system and not to discuss the implementation issues. It is white box view. If we discuss about implementation issues, then it is white box view. The SRS document should view the system to be developed as black box and should specify the externally visible behavior of the system. For this reason, the SRS document is also called the black box specification of the system, which means we are not going to get into the details of how this process is happening. We are just going to say, I am going to give input, I needed this output. Not going to discuss, not going to not going to take care of implementation. And then conceptual integrity. It should show conceptual integrity so the reader can easily understand. And then response to undecided events such as exception handling. It should characterize acceptable response to undesirable event, like manuals. In later parts, we have to give manuals how to solve like recovery issues, compatibility issues, portability issues. So these are called system response to the exceptional conditions, and it should be verified. There is a verification should be done in the end, like acceptance testing. During acceptance testing, the customer verifies the SRS document so he can check whether what they requested. All requirements of the system as documented in the SRS document should be verifiable. This means that it should not be possible to determine whether or not requirements have been met in the actual implementation. What are the problems without an SRS document? The important problems organizations face that it does not develop a document here is without developing an SRS document, the system would not be implemented according to the customer needs. The developers would not know whether what they are developing is what exactly required You know why this happening again and again after 8 p.m. I'm so confused with the Zoom. Like it is reconnecting. I did everything in possible way in technical manner that what can be done for the Zoom meeting. Nobody can able to understand how this is happening after 8 p.m. It is just reconnecting itself again and again and again. I'm just fed up with this Zoom meeting. We can just go switch back to Zoom, Google meeting, but we cannot be able to record. That's the only problem. Without SRS document, it will be very much difficult for the maintenance engineers to understand the functionality of the system, because we knew that 60% of the entire software product life is uh, lies on maintenance. In order to maintenance, we need a proper document to verify and check. It will be very much difficult for user document writers to write user manuals properly without understanding the SRS document. Problems with an unstructured specification. It would be very much difficult to understand the document. It would be very much difficult to modify the document. Conceptual integrity in that document would not be shown. The SRS document might be unambiguous and inconsistent. Okay. Okay. So we can